This is Lecture 2 of Module 10 in the book Problem Solving Guide for Mechanics and Thermodynamics. The topic is phase changes and the energy associated. So in the previous lecture we covered the energy to change the temperature of matter. Here we cover the energy needed to change the phase of the matter. The temperature will not change. The heat of fusion is the amount of energy needed to take an amount of substance from a solid to a liquid as its melting point. So no temperature change, or liquid to a solid. Heat of vaporization is the amount of energy needed to take a liquid at its boiling point to a gas at its boiling point. So no temperature change, just a phase change. The SI unit of heat of fusion is joules per kilogram. Notice there's no change in temperature there. SI unit of the heat of vaporization is also joules per kilogram. The amount of energy per kilogram to change the phase. There's no delta T. So to fundamentally understand what's going on, it's important to understand that the atoms of a material have a distribution of speeds at any given temperature. We covered this in the first lecture for this module. So here's the probability density function for the speed of atoms of helium at 300 kelvins. So the temperature is 300 kelvins, but the speed of the helium atoms have a tremendous range. Peaks around 1,200 meters per second, something like that. Some of them are going 3,000 meters per second, 3 kilometers per second. Some are moving very slowly. This is what the distribution function looks like, a range of speeds in a gas. The gas is at 300 kelvins, but there's a range of speeds. Same is true in a liquid and a solid. There's a range of speeds at a given temperature. If you have a pot of water, some of the molecules are moving very fast compared to the others. It's natural. There's a natural distribution of speeds. When the atoms are banging into each other randomly, there's going to be a distribution of speeds. So let's take an empty container, empty, no air, it's a vacuum, and fill it half full with water and then seal it. What happens? There's our container. Well, some of those water molecules are moving fast. And when they hit the surface, they can escape. They're going to go into the gas phase. So there's going to be some water vapor in that space. So some of them are going in, some of them are going out. There's going to be an equilibrium reached. So that's called the vapor pressure. The pressure in this space is the vapor pressure of water at that temperature. Now if you heat up the water, more of the water will go into the gas phase. At room temperature, the vapor pressure of water is only 1/40th of atmospheric pressure. But as you heat up the water, the pressure is going to go up. The vapor pressure increases. More and more of the atoms, you're shifting that distribution to higher and higher speeds. When the vapor pressure of the water reaches the pressure of the atmosphere, that's the definition of the boiling point. And if the container is not sealed, the atmosphere above it is dry, all the water is escaping and not coming back. It's going to evaporate. The faster ones go first. And this is important to understand. When the fast ones leave, the kinetic energy of the remaining molecules goes down because the fast ones left. If you have a distribution of test scores and you take away all the scores that are above 90%, the average of the remaining is going to go down. And this is called evaporative cooling. If you take away the hot ones, the new average is going to be lower. This is how the human body prevents overheating. It sweats. When the sweat evaporates, it's the fast ones that go. And it leaves the low kinetic energy, the colder ones, behind. And the process is faster if you have a fan and you blow the air, and if the air is dry. It's much harder to cool off the human body when it's humid out because the air already has a bunch of water in it. If you stand in front of a fan after taking a shower, that's going to cool you off very quickly. In England, butlers are trained to cool the wine for a picnic by wrapping a wet towel around it and holding it out the window of the Bentley while driving fast. That's how you cool things off. In the old days, cars would drive around with canvas bags of water attached to the outside of them. I'm old, but I'm not this old. So here's a bag drive around fast. It's a canvas bag. Some of the water is going to leak through and evaporate, and that's the hot ones. So the water in the bag is going to be nice and cool, even on a hot day. In the hot fields of Spain, workers have a botillo with them. It's porous clay, so the water seeps through the walls, and the hot ones leave, leaving the cool ones. Natural air conditioning. In the Australian outback, when it's really hot, the kangaroos lick their forearms to cool off. They have a lot of blood vessels near the skin, the surface on the forearm, so when the spit evaporates, they cool off. Cools their blood. A common explanation you can find online for evaporative cooling uses the fact that water will absorb large amount of heat in order to evaporate. If you understand how the process works, I don't think you're going to say that. Water absorbs heat in order to evaporate. The simple fact is there's a distribution of speeds, and the fast ones are more likely to leave than the slow ones. And when the fast ones leave, the ones that remain are slower, of course. This reduces the average speed of the remaining molecules. So now we can talk about heats of fusion and heats of vaporization. So there's no temperature change involved, only a phase change. The numbers for water are enormous. Once you see these numbers, you'll understand why a kangaroo licks its forearms. So it takes 4,184 joules to change 1 kilogram of water by 1 degree Celsius. It takes 2,260,000 joules to take 1 kilogram of liquid water at 1 degree Celsius to a kilogram of water vapor at 100 degrees Celsius. So you're just changing the phase, not even changing the temperature. So the latent heat of vaporization of water, 2,260,000 joules per kilogram. This is more than 5 times the energy it takes to take 1 kilogram of liquid water from 0 to 100, all the way, 100 degrees. It takes 5 times more energy to boil it than it does to take it from 0 to 100. The heat of fusion of water is 334,000 joules per kilogram. So 334,000 joules to take ice at 0 to water at 0. If you want to freeze the ice, you got to take out 334 joules per kilogram to go from 0 degrees water to 0 degrees ice. That's the latent heat of fusion of water, 334,000 joules per kilogram. These are called latent heats because latent is Latin for hidden. It's called latent because there's no temperature change. So you're putting energy in and the temperature is not changing, or you're taking energy out and the temperature is not changing. The phase is changing. So let's do a hard problem that incorporates both a temperature change and a phase change. This is a complicated problem. It's going to take a while. You should probably have a piece of paper and a pencil. It's going to be hard to follow just by watching it. You might have to watch it a few times. So we have a 10-gram ice cube. It's at -5 degrees Celsius, placed in an insulated mug that's 100 grams of water at 20 degrees. And then we put the lid on. What's the equilibrium temperature? 10 grams of ice at -5, 100 grams of water at 20. Put the lid on. What happens? So we have to do these problems in multiple steps, and we have to be careful because we don't know if all the ice is going to melt. Maybe there's going to be some ice left over. We don't know. We got to figure it out. We have to range find. So a good first step is to determine the amount of energy it takes to take ice at -5 to ice at 0. No phase change. All right, so we have Q as mc delta T, and it's ice, so we use 2,093 joules per kilogram per degree Celsius. We have a 100th of a kilogram, 10 grams, and we're going 5 degrees. That costs 104 joules, and we're going to get that from the water at 20 degrees Celsius. That's where it's going to come from. Next, we're going to see how much energy it takes to melt 10 grams of ice. Maybe there's not enough in this 100 grams of water at 20 degrees, but we're going to find out. So Q is M, the mass, times the latent heat of fusion. We have 100th of a kilogram, so it's going to cost us 3,340 joules to take ice at 0 to water at 0. Now we're going to see how much thermal energy we can get out of the water at 20 to see if we can melt the ice. So we're going to check if we have enough to take, if we take the water at 20 to water at 0, how much are we going to get out? If it's more than this, then we can melt all the ice. And it turns out Q is MC delta T. We have 1/10 of a kilogram at 20 degrees Celsius. And if we go all the way to 0, the temperature change is 20, and that's going to get 8370. And that's more than enough to melt the ice. So all the ice is going to be melted. So we don't need this anymore because we don't know that it's going to go all the way down to 0. Here we're saying that the temperature change is 20 degrees of this 100 grams. But it's not going to be because all the ice is melted. So the next step is determine the final temperature of the 100 grams of water after taking this much energy from it. Because it's going to cost this much energy to go from -5 to 0, and then ice at 0 to water at 0. So we're calculating the delta T of the 100 grams. This is liquid water. We're going to take 3440 out of it, and we're going to find the temperature change. When we calculate the temperature change, it's 8.22. This is the delta T. It starts at 20, and it's going to drop 8.22 degrees Celsius when taking that ice from -5 to 0 and then melting it. So now we have 100 grams of water at 11.8 degrees, and we have 10 grams of water. Remember, we melted it, and it's at 0 degrees. We didn't change the temperature yet. So now we have to calculate the final equilibrium temperature of 100 grams of water at 11.8 and 10 grams of water at 0. Okay, so the energy is going to be transferred from the hotter water to the colder water until an equilibrium is reached, and we can calculate it. The thermal energy lost by the water at 11.8 is this. Now we don't know what T final is, but we know the temperature change is 11.8 degrees Celsius minus T final. And it's 100 grams. This is the water at 11.8. There's this specific heat of water. The thermal energy gained by the water at 0, this is 10 grams of water at 0, 10 grams, it's water, and its final temperature, its temperature change is T final minus 0, which of course is just T final. These are equal, they're both positive. I arranged them so they're both positive. 11.8 minus T final minus 0. And we have one equation and one unknown that we can solve. The thermal energy lost by the 100 grams of water at 11.8 degrees Celsius is this. So we're just going to multiply through this term, that term, and then this term, and then the T final. This is what it looks like now. We have a constant term and a term with T final. The thermal energy gained by the 10 grams of water at 0 is this. We're going to multiply these through. And we get just this because we have a 0 here. Multiplying this 2 by 0 gives us a 0, so we only have this term. Now we can set the magnitudes of these two equal, and we can solve for T final. We can collect the T final terms, divide by 460 joules per degree Celsius, and we get 10.7 degrees, and that's sort of as expected because there's 100 grams at 11.8 and only 10 grams at 0. It's going to end up a lot closer to 11.8 than it is at 0. They have the same heat capacity. They're both liquid water. We could have just set up a proportion, but let's do it so you can use it to solve any problem. So the key to success in solving multiple step problems like this is to understand what's going on with the Q's and be very careful and methodical so you don't make errors, especially algebra errors. There's a lot of algebra involved here. So you need to practice so you get it right. Go.